Welcome to Lesson 1C, Chemistry Review. I'm going to start by showing some common acronyms that we'll use throughout the course, and then we'll talk about molecular weight, ideal gases, and stoichiometric mass balance. We will use all of these acronyms throughout the course, so it would be good for you to learn these things. EPA, DEP, etc. You can read these. I'm not going to read them all to you. So I want to start by review of chemistry. So this should all be reviewed, but my notation may be different than you're used to, and I'm very much a stickler for units, so I may say things a little differently than you're used to. They expect us to remember stuff from past courses. Yeah, this ain't grade school no more, bro. So capital M is molecular weight, and this will be common notation throughout all my courses actually. So when I use squiggly brackets around something, it means the dimensions of. So the dimensions of capital M are mass per mole. And then I use square brackets to mean the units of. So the units are typically kilogram per kilomole or gram per mole. A kilomole being 1,000 moles, just like kilogram is 1,000 grams. And so, for example, C is carbon, one of the elements. And if you look up MC on the periodic table, there is a periodic table, by the way, on our website that you can point to under references and links. And putting in a lot of significant digits, as many as I see there, is 12.0107. Sometimes people call this AMU, atomic mass units, but that is the same as 12.0107 grams per mole. So we're going to always use grams per mole as our molecular weight instead of AMU, which is kind of a strange unit. And so I'll just point you to the periodic chart on our website. We know also that 1 mole is equal to 6.0225 times 10 to the 23 molecules. A mole of carbon if it's by itself, a mole of oxygen by itself, or a mole of a molecule like O2 or CO2. So this would be a number of moles of that molecule, number of moles of that, number of moles of that. So it doesn't matter if it's a molecule or an element, we still talk about a mole being this amount, which is Avogadro's number, which you should have remembered from chemistry. And so in my notation, I let N equal the number of moles. I will also let M equal the mass. This is a lowercase m as opposed to a uppercase m here for molecular weight. So little m is mass. The equation between them is the mass is N times the molecular weight. Keeping with my units, I like to do this for most of the things I define. So obviously the dimensions of mass are mass, and the units of mass can be kilogram, gram, milligram, microgram, whatever mass units you want. And then the dimensions of moles are just mole. Some people use a MOLE, I use MOL. And of course, the units of N are also mole. So mole is a unit. It's not really a mass, it's amount of matter. Doctor, please help. I woke up with this strange looking mole on my hand. Some useful molecular weights. Capital M of air is equal to 28.97 gram per mole, or kilogram per mole if that unit is better for you in a particular problem. You can always convert between grams and kilograms. And then sometimes we'll use water, 18.02 gram per mole. And these are both on the equation sheet, and the equation sheet is very useful for you to use throughout the course. So I'd highly recommend that you print that out. All right, let's look at the ideal gas law. The ideal gas law, PV equal mRT or PV equal nRUT, either one of those. And by the way, my notation, which I also do in all my courses, V is volume. I put a line through it, and V is a speed or velocity. When I put a line through it, that means volume to distinguish those V's. When I wrote my fluids book, I used a different font for V. So some of you are familiar with that kind of script looking font for volume, whereas V is just the normal Times Roman font. So here, RU is called the universal gas constant, and RU is equal to 8.314 joule per mole K. And you can also write that as 8.314 kilojoule per kilomole K. So either of these is acceptable. Just use the one that is easiest to use in your whatever equation you're using. The dimensions of this universal gas constant is an energy per mole per temperature. And the units of RU are joule per mole K, as you see here. So that's the universal gas constant. Contrast that with R by itself, called the specific gas constant. You can think of it like thermodynamic specific per unit mass, or you can think of it as for a specific gas or a particular gas. So the difference is the dimensions of R are energy. Instead of per mole, it's per mass and temperature, and the units are joule per gram K or kilojoule per kilogram K. And the equation for R is equal to RU over molecular weight M. You can verify the units of R by plugging units into here and using this equation also to convert from mass to number of moles, and vice versa. You can prove that this is true. For example, let's take air, since we're talking about air pollution, and air will be the main gas in this course, which we're assuming is an ideal gas. So R of air is equal to RU over M of air, 8.314 kilojoule per kilomole K over 28.97 kilogram per kilomole. Kilomoles cancel, as you see there. This turns out to be 0.2870 kilojoule per kilogram K. So I just want to make a couple comments here. First of all, some books don't distinguish between RU and R, and I find that very confusing. So I will always distinguish between RU when there's some chemical like air. Here, that's the R of that specific chemical, and RU is universal for all ideal gases. Another comment is about equations. When you do any kind of calculations, always put in your units, and units are definitely important in this course and in all courses in all walks of life. As you become an engineer, always put in your units, make sure your units are consistent with your answer. You'll save yourself a lot of trouble in life by doing that. Another comment, just looking at these equations, I had given you these ideal gas relations. So PV equal MRT, but we know that M equal N times capital M. So we can write this PV equal NMRT. But R is equal to RU over M. So we have PV equal NM RU over M. T, the M's cancel out. So we get PV equal N RUT. These are both valid expressions of the ideal gas law. Stoichiometric mass balance. This is again a quick review of chemistry, so I'll just do a very easy example here. The basic statement of this is that mass must be conserved for each element in any kind of chemical reaction. So I'll give you a quick example. AN2 plus BO2 equals CNO. And instead of the equal sign, chemists like to use an arrow, so we can use an arrow. That's fine, like that if you prefer. By the way, NO is nitric oxide compared to N2O, which is nitrous oxide, and nitrogen dioxide is NO2. We put those all together and call them NOx, NOx, where X is either 1, 2, or the N sometimes is 1 or 2. All these guys, these A, B's, and C's, are called molar coefficients. You can think about this equation. These A, B, and C's can either be individual molecules. So A molecules of N2 plus B molecules of O2 yields C molecules of NO. Or what we typically do is think of them as moles instead. The dimensions of A and B and C are just mole. So A moles of N2 plus B moles of O2 equals C moles of NO. So we call these molar coefficients. To conserve mass of each species, so unless you have some kind of nuclear reaction going on where the elements actually change from one to another, or change to different isotopes, or uranium decays into lead and stuff like that, we're not talking about anything like that. So you just take each element and you look at the equation. So we have 2N's times A, so we would call this 2A. On the left, there's no other A's in the second term, equal, and then there's a Cn on the right. So 2A equals C, so C equal 2A. And then for the O, we only have two elements in this simple equation. We have 2 O's times B, so 2B equal C, so C equal 2B. From this, we can conclude that A equal B. Well, how can we solve this? Well, we're stuck because we have three unknowns, A, B, and C, but we only have two equations, one for N and one for O. So how do you do this? Well, you need to pick something. You can pick whatever you want. Usually we pick something nice like 1, and therefore from these two equations, B is equal to A, so B equal 1, and C is equal to 2A, so C equal 2. So then we would write A equal 1, N2 plus B equal 1, O2 yields C equal 2, NO. You could do that in your head, since it's such a simple equation. But I just want to point out that you could pick a different A. A doesn't have to be an integer. None of these molar coefficients have to be integers. So with that, we'd have B equal 1/2 and C equal 1. So our equation would be 1/2 N2 plus 1/2 O2 yields NO. These are both correct. Pick the one that works best with whatever else you're doing. You usually don't pick something like 3.821 for A. You pick 1/2 or 1 or 2 typically when you have to pick one. Let me conclude with a simple example here. For the case of ideal combustion of propane, we have 1 mole of propane reacting with A moles of oxygen molecules to form B moles of carbon dioxide molecules and water vapor. So write out the stoichiometric equation and solve for coefficients A, B, and C. First of all, I need to look up the chemical equation for propane. So you just jump on the internet and get that. It's C3H8. And then the equation I would set up for 1 mole of propane, so that coefficient here is 1, plus A moles of oxygen, so AO2 yields B moles of CO2 plus C moles of water vapor. And now we do the mass balance. This is our chemical equation. We just need to find A, B, and C. So doing this mass balance for carbon, I have 3 equal B, and you can see that from here, 3 C's there, and then a B, C there. So B equal 3, H, 8 on the left, and there's 2 times C on the right. So C equal 4. And then for O, we have 2 A's, we have 2 B's, and we have 1 C, so you can write it out that way. When you solve this, you can solve this for A equal 2B plus C over 2. Plug in these guys and you get A equal 5. So the final chemical equation will be written as, plugging in all these coefficients, CH8, that's our propane, plus 5O2 yields 3CO2 plus 4H2O. That's our water vapor. By the way, this is ideal, or what we call stoichiometric combustion. It's ideal in that we are taking all of our carbon on the left and converting it to carbon dioxide on the right. There's no other air pollutants in here. We have just CO2 and H2O. H2O certainly is not an air pollutant. CO2 is not an air pollutant. It is a greenhouse gas. So that's called ideal or stoichiometric combustion. If you had non-ideal combustion, then we either have too much or too little oxygen in the combustion of this fuel, which happens to be propane here. And so what happens is this coefficient, which we called A would not equal 5. It'll be either too small or too big. And then you get other stuff coming out. So this generates air pollutants. A common one would be carbon monoxide or soot. And then you can get other aldehydes and alcohols and other things like that. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.